Hi, I am Oren and I'm glad to present our paper, Visual Editing with LLM-based Toolchaining. This is joint work with Lightricks and the Hebrew University of Jerusalem, Israel. Videos are a popular storytelling medium. However, the complexity of video editing with its numerous parameters and their interactions possess significant barriers for beginners. Using natural language can mitigate this challenge. Text-to-video diffusion-based models have demonstrated impressive results. However, they are computationally expensive, slow, and still lack visual quality and user control over the generated video. We believe that instead of relying on end-to-end approach that treats deep learning models as black boxes, it is more beneficial to teach LLMs to use the existing specialized tools. This approach is also more interpretable. Our idea is to teach LLMs to use the existing specialized tools in our video editing app, VideoLeap. Our goal is to implement an AI assistant democratizing advanced capabilities. As a proof of concept, we focus on the tonal color adjustment tasks, which allows users to change a video's appearance via textual instructions. Here is an illustration of our tasks. Users input an image or a video and specify the desired visual appearance. In the upper row, we have the source images, and in the middle, we have the user intents. An LLM interprets these intents, select tools, and set parameters. The bottom row displays the generated images by applying the LLM's outputs in our app. For example, inputting Morocco on the left results in a warm hues typical of Moroccan landscapes reflecting its deserts. Our application offers three tonal adjustment tools: Global Adjust for global color range, Selective Adjust for selective color range, and Filters. Each tool has up to a dozen of parameters which can be difficult for beginners to set correctly. For example, consider an input image with a request for a golden hour look. Here the temperature has been increased to add warm golden tone to the image. The reds, orange, and yellows have been enhanced to create the warm golden hour look. Additionally, the faded high noon filter has been applied. By utilizing these tools with the specified parameters, the generated image captures the essence of the golden hour look. In our proof of concept, we found that proprietary LLMs like GPT 3.5 Turbo can solve this task using preliminary prompts. However, their high cost and latency make them unsuitable for real-time industry applications. To overcome these limitations, we propose a distillation framework approach where we fine-tune a smaller student LLM with guidance from a larger teacher LLM and user behavioral signals. Our approach has the following advantages. Our fine-tuning involves an open-source LLM, which is free, a smaller LLM for better latency, and it learns from high-quality data to better align our users' preferences. Here is a diagram of our distillation framework approach. We first generate data by collecting outputs from a teacher LLM based on user intents. The teacher LLM selects relevant tools and sets their parameters. If multiple users express the same intent, this could result in multiple outputs per intent. We ensure high-quality data by retaining the best results based on user feedback, filtering out those with no engagement. The retained data samples are injected into prompts for fine-tuning and are randomly split into training and test sets. Then we fine-tune a much smaller student LLM on this dataset. Since comparing between fine-tuned models in an online A/B test is costly and takes time, we design offline evaluation metrics to predict the model's performance online. To improve fine-tuning in low data settings, we use augmentation by having another LLM generate similar samples for those the student LLM got wrong during training, then add these to the training set. Finally, to compare the actual performance of two fine-tuned student LLMs, we conduct an online A/B test. Now I would like to add more details on our offline and online evaluation metrics. Our offline metrics assess two key elements of the task. First is tool selection, which measures the model's ability to decide correctly whether to use a tool. We measure precision and recall and report tool selection score as F1 score. Second is quality, the model's ability to use a tool correctly. For the filter tool, the quality score is the accuracy, the proportion of correct predictions between the predicted and ground truth filter names. For the adjust and selective adjust tools, the quality score is the mean cosine similarity across samples on predicted and ground truth parameter values. Note that this metric is overly strict, as a desired result might be achievable with different parameter combinations. The final score for a tool is the harmonic mean of the tool selection score and quality score, emphasizing high performance in both. And finally, we have the overall score, which is the average of the final scores of all tools. In addition, we have a reality check to analyze the actual generated images or videos by applying the tool's predicted parameters in our app. In this study, we analyze a random sample with 3 human annotators per sample. When our offline evaluation shows it is worthwhile to consider a new student LLM, we confirm it in an online A/B test experiment. Our metric of interest for our online A/B test is the project completion rate, which is the number of projects exported divided by the number of projects started. This metric indicates the total user satisfaction with the results and the overall experience. Now let's see the results. We ask 2 research questions. First, how well the student LLMs perform, and do they effectively mimic the teacher LLM? Second, is augmentation effective in low data regimes? Our models for experiments are GPT 3.5 Turbo as the teacher LLM and the student's LLM Llama 2 7 billion chat and Flanty5 base, which is even smaller. In research questions 1, we found in our offline evaluation on the test sets that Llama 2 7 billion chat and Flanty5 base perform very similar in terms of overall accuracy, which is the average of final scores across the tools. In our reality check on the generated images by applying the LLM's outputs in our app, we ask the annotators 2 questions per sample. First, is the image relevant to the intent? And second, does the student model correctly mimic the teacher? We report the majority vote between annotators and found that the teacher and both students achieve very good results, 13 to 14 relevant results out of 15. And both student LLMs perform similarly, mimicking the teacher correctly 11 out of 15 times. We conducted 2 online A/B test evaluations and found that both student LLMs, Llama 2 7 billion chat and Flanty5 base, succeeded in matching the performance of the teacher LLM GPT 3.5 Turbo. We are encouraged by the fact that our offline metrics align with the results of the online A/B tests. We also show a 25% improvement in fine-tuning in low data regimes using data augmentations. Read the paper for more details. To conclude, we presented a novel NLP application for automatic video editing using LLMs. By fine-tuning a student LLM with guidance from a larger teacher LLM and user behavioral signals, we achieve similar performance to GPT 3.5 Turbo both in offline and online experiments. Our solution significantly reduces costs and latency, crucial for industry applications. Here is a link to our paper website. See you in Miami. Thank you.